To determine process parameter of laser cutting machine, a review. Abstract, laser, light amplification by stimulated emission of radiation, cutting is one of the best technology developed for the cutting, drilling, micro-machining, welding, sintering and heat treatment. It is one of the thermal energy-based unconventional process used for cutting of complex profile materials with high degree of precision and accuracy. All cutting parameters have significant influence on quality work. The aim of this study is to relate the CO2 laser cutting parameters such as laser power and cutting power. The laser beam is typically 0.2 mm in diameter with a power of 1 to 10 kilowatts. Depending on the application, selection of different gases are used in conjunction with cutting. Increasing the frequency and the cutting speed, decrease the kerf width and the roughness of cut surface, while increasing the power and gas pressure increases the kerf width and roughness. The relation between the input parameters and the response were investigated. The performance of laser cutting process mainly depends on laser parameter. Keywords: laser cutting, surface roughness, process parameter, kerf width, CO2, heat affected zone. 1. Introduction. In recent time, technological advancement can be seen in every area. Laser cutting works by concentrating a high-power pulsed laser at a specific location on the material to cut. The energy beam is absorbed into the surface of the material and the energy of the laser is converted into the heat, which melt or vaporize the material. It is a non-contact operative method, hence a good precise cutting of complex shapes can be achieved. It can cut process material like ferrous metal, non-ferrous metal, stone, plastic, rubber, and ceramic. There are many advantages of laser cutting over mechanical cutting. Since the cut is performed by the laser beam, there is no physical contact with the material, therefore contaminants or impurities cannot enter or get stuck into the Bhaumik Patel 4. Student. Department of Mechanical Engineering, LDR-PITR. Gandhinagar, India. Saumil Patel 6. Lecturer. Department of Mechanical Engineering, LDR-PITR. Gandhinagar, India. Material. The advantages of laser cutting include high productivity thanks to the high cutting speeds, narrow kerf width which leads to minimum material lost, straight cut edges, low roughness of cut surfaces, low metallurgical distortions, and easy integration. The two main laser sources which are widely used in laser cutting are CO2 and ND-YAG lasers. ND-YAG laser is an optically pumped solid-state laser, working at a wavelength of 1.06 CO2 laser is an electrically pumped gas laser that radiates at wavelength of 10.6 m. The main operating parameters associated with laser-used machining are laser power, spot diameter of the laser beam, cutting speed, feed rate, and depth of cut. The cut quality traits like edge surface roughness, RA, and surface hardness are considered as output parameters. The cut edge is cooled by the gas flow, thus restricting the width of the heat affected zone, has. Maximization of the productivity and the cut quality along with minimization of costs are goals of manufacturers with a limited theoretical and practical background to assist in systematical selection. Laser process parameters are usually chosen on the basis of handbook values, other manufacturers' recommendations and by previous experience. Improper selection of cutting parameters cause high manufacturing costs, low product quality and high waste. The performance of laser cutting process mostly depends on laser parameters. By proper control of the cutting parameters, good quality cuts are possible at high cutting rates. Therefore, it is important to investigate the impact of cutting parameters on quality of cut. 2. Working principle: laser cutting is a thermal, non-contact, and highly automated process well suited for various manufacturing industries to produce components in large numbers with high accuracy and surface finish. The highly flammable oxidized gas from the gas cylinder comes in the nozzle where it gets ignited with the amplified light and produces the high intensed flame which imparts on the material, and due to that the cutting action on the material takes place. This high intensed flame may be of different gases, mainly the gases used are CO2, O2, N2, etc. Depending on the cutting parameters, different gases with pressure are adjusted to produce the flame. The main objectives of this flames are sublimating, melting, and burning. The cutting process is executed by moving focused laser beam along the surface of workpiece at a constant distance, thereby generating a narrow cut kerf. This kerf fully penetrates the material along the desired cut contour. This process is successful only if the melt zone completely penetrates the workpiece. Laser metal cutting is therefore generally restricted to thin section. While cutting has been reported through 100 mm sections of steel, the process is more typically used on metal sheets 6 mm or less in thickness. 3. Process parameter: the laser cutting has been a major area of research for the cutting of the metals. The various parameters affecting the cutting quality like cutting speed, focal point, laser power, gas pressure, etc. The various parameters are listed which affects the cutting process. 3.1 Surface roughness. It is the effective parameter representing quality of a machine surface. K. Agani and M. Nuishi 5 predicted that with the increase in cutting speed and frequency and decreasing laser power and gas pressure, roughness reduces. The laser cut surface reveals a specific for of unevenness. 3.2 Kerf width. The measure of portion cutaway by laser is known as kerf. The portion of cut is known as kerf width. The kerf width refers to the width of slot that is formed during through thickness cutting and is normally narrower at bottom surface of workpiece than at the top surface. The kerf width shows the size of the cut and the amount of material wasted, therefore small diameter of laser is required for the less wastage of material. The width of the cut kerf corresponds to circular beam waste size, which is determined mainly by the laser beam quality and focus optics. 3.3 Heat affected zone. HAZ. The HAZ is something that occurs when metal is subjected to high temperature. It has negative impact on the design and structure of the metal. With the mechanical cutting, the shear strength of material surpassed. The majority of the energy converts into heat that influences both lifespan of the tools and metal to be cut. As increasing gas pressure and cutting speed results in an increase of HAZ width. As the gas pressure increases, the power produced due to the exothermic reaction becomes higher and produces higher HAZ width. The increase in laser power and standoff distance results in decrease of HAZ width, but their effect seems to be negligible than the effect of cutting speed and gas pressure. 3.4 Cutting speed. The cutting speed must be matched to the type and thickness of the workpiece. A speed which is too fast or too slow leads to increased roughness, burr formation, and to large drag line. The energy balance for the laser cutting process is such that the energy supplied to the cutting zone is divided in two parts, namely, energy used in generating cut and the energy losses from the cut zone. It is shown that the energy used in cutting is independent of the time taken to carry out the cut, but the energy losses from the cut zone are proportional to the time taken. Therefore, the energy lost from the cut zone decreases with increasing cutting speed, resulting into an increase in the efficiency of the cutting process. The cutting speed must be balanced with the gas flow rate and the power. When oxygen is applied in mild steel cutting, too low cutting speed results in excessive burning of the cut edge, which degrades the edge quality and increase the width of the heat affected zone, HAZ. The speed must be decreased when cutting sharp corners with a corresponding reduction in beam power to avoid burning. The cutting speed for a material is inversely proportional to its thickness. As from the derived formula by 6 mm Nor, K.Cat Gamma and mm Raman, keeping power and tip distance constant and varying the speed of the nozzle. The Ra value obtained are shown in figure 3.4. 3.5 Laser power. The laser power must be adjusted to suit the type and thickness of the workpiece. A reduction in the laser power may be necessary to achieve high accuracy on complex-shaped workpieces or very small parts. Laser power is the total energy emitted in the form of laser light per second, while the intensity of the laser beam is the power divided by the area over which the power is concentrated. High beam intensity, obtained by focusing the laser beam to a small spot, is desirable for cutting applications because it causes rapid heating of the kerf, leaving little time for the heat to dissipate to the surrounding, which results into high cutting speeds and excellent cut quality. Additionally, reflectivity of most metals is high at low beam intensities but much lower at high intensities, and cutting of thicker materials requires higher intensities. The optimum incident power is established during procedure development because excessive power results in a wide kerf width, a thicker recast later, and an increase in dross, while insufficient power cannot initiate cutting. High power beams can be achieved both in pulsed and continuous modes. However, high power lasers do not automatically deliver high intensity beams. Therefore, the focusability of the laser beam is an important factor to be considered. 3.6 Gas pressure. The material workpiece thickness must be matched to the gas pressure. When torch cutting, thin metal material is cut with higher gas pressure than thicker material. The pressure of gas must be regulated carefully, because the quality of cut is affected by even slight changes in the pressure of gas. If the pressure is too low, the fluid slag remains adhered to the base material, forming a permanent burr or closing the kerf again. If the pressure is too high, the lower edges of the cut are burnt out and often make the cut unusable. In contrast, very high pressure cutting thicker workpieces are work at higher gas pressure. 3.7 Nozzle diameter and standoff distance. The nozzle delivers the cutting gas to the cutting front, ensuring that the gas is coaxial with the laser beam and stabilizes the pressure on the workpiece. The nozzle orifice determines the shape of the cutting gas jet and quality of cut. Mainly the diameter of nozzle ranges from 0.8 mm 3 mm. Due to the smaller size of beam, the cut kerf is often smaller than the diameter of nozzle. This distance influences the flow patterns in the gas, which have a direct bearing on the cutting performance and cut quality. Large variations in pressure can occur if the standoff distance is greater than about 1 mm. A standoff distance smaller than the nozzle diameter is recommended because larger standoff distances result in turbulence and large pressure changes in the gap between the nozzle and workpiece. With a short standoff distance, the kerf acts as a nozzle and the nozzle geometry is not so critical. For literature review. In 2008, Avanish Dubey in laser beam cutting, LBC, process, it has been found that the kerf width during LBC is not uniform along the length of cut and the unevenness is more in case of pulsed mode of LBC 8,14. In this paper, two kerf qualities such as kerf deviation and kerf width have been optimized simultaneously using Taguchi quality loss function during pulsed ND, YAG laser beam cutting of aluminium alloy sheet, 0.9 mm thick, which is very difficult to cut material by LBC process. A considerable improvement in kerf quality has been achieved. In March 2015, Matic has been worked on an experimental analysis and optimization of CO2 laser cutting process on stainless steel plates. In this paper, multi-objective optimization of the cut quality characteristics such as surface roughness, width of has and kerf width in CO2 laser cutting of stainless steel. The applied methodology integrates modeling of the relationships between the laser cutting factors, laser power, cutting speed, assist gas pressure and focus position, and cut quality characteristics using ANS, formulation of the multi-objective optimization problem using weighting sum method and solving it by CSA, comparative sequence analysis. Cuckoo search method is used for optimization purpose. 3 Yuzof et al., 2008, have found that at all cutting speeds, the kerf width increases by increasing the laser powers while sideline length and percentage over length decreases by increasing laser power. Increasing the cutting speed in pulsed mode led to rough surface and incomplete cutting while in CW mode, increasing the cutting speed with equivalent increase in power, led to better quality and smoother cut surface up to 8m/min cutting speed. The SR also increases by increasing the peak power, gas pressure, pulse frequency, and duty cycle. The surface roughness of the cut specimen can also be changed by changing spot overlap and pulse width. In 2006 Miroslav and Predrag has worked on surface roughness by laser cut. Quality is very important. Observation of the cut surface can reveal two zones, the upper one in the area of the laser beam entrance side and the lower one, in the area of the laser beam exit side. The former is a finely worked surface with proper grooves whose mutual distance is 0.1, 0.2 mm while the latter has a rougher surface characterized by the deposits of both molten metal and slag. Standard roughness RZ increases along with the sheet thickness, but decreases with increase of laser power. By cutting with laser power of 800 W standard roughness R is 10 m for sheet thickness of 1 mm, 20 m for 3 mm, and 25 m for 6 mm correlation, which connected the standard roughness, 10-point height of irregularities, and mean arithmetic profile deviation. The linear and exponential relationships can be used. In 2012 Sniana Radonjic and Pavel Kovac has defined process parameter of laser machine. Experimental research carried out during laser processing of AISI 314 resulted in an optimal cut. The optimal cut is obtained using the following processing parameters: feed rate 1250 mm/min, laser power 4400 W, focal point 16 mm, gas pressure 17 billion Argentine pesos and nozzle distance 7 mm. In August 2011 B.S. Yilbas has researches on laser hole cutting into Ti6Al4V alloy and thermal stress analysis. In April 2012 Martin GREPL1, Marek Pag degree researches on laser. A.C1, Jana PETRU1. Cutting of materials of various thicknesses. And found upon that suitable parameters for cutting Haynes. To avoid any influence of the surrounding atmosphere on the cut, it is suitable to measure the recast layer using a microprobe, and then to perform a microchemical analysis. We recommend that increased attention be paid to a study of the recast layer and its increased dependence on cutting parameters. It would be suitable to perform the microhardness measurement at the melting boundary of the original material, and more importantly, on the recast layer itself. Our paper has contributed a comprehensive view on the influence of the process parameters on a narrow group of materials used in the aerospace industry. 5. Conclusion. By referring different review and research paper we can conclude that with the changes in the power the roughness of the material decreases, while the gas pressure also has great effect on the surface roughness, but with the high speed the roughness increases any may leads to the increase wider kerf width. For different material different gases are used. This parameter has a wider impact on the material roughness and surface finishing. Mainly the CO2, O2, and N2 are mainly used for the cutting process, but with the use oxygen gas the surface may sometimes the material gets cracked and leads to failure of workpiece. Gas pressure has a major effect on all the quality parameters, i.e., has width, kerf width, and roughness.